So here's the setup for finding the potential finite line charge of uniform charge density. We looked at the field and the potential along the z-axis here, right in the middle of this line charge. Now what we'd like to do is examine the potential at a point off the axis, see if we can also extend this to 3 dimensions. So what we need are the vectors. So we look at the vector that connects the origin, which is right in the center of this charge density, to the point xy, that we call r. Coordinates are just xy for this vector here. Down here we have the vector r prime, which connects us to our little charge element, which for a linear case would be lambda dx prime. So then we take the difference vectors, so we take r minus r prime, which is right here, and that'll be the vector that goes from the little charge element to the point where we're trying to find the potential. So that's going to give us a little differential of potential, and we're going to end up integrating over that to get the complete potential. So here's my translation. If you take the vector r and express it in Cartesian coordinates, here's the x component right here, here's the y component. The r prime component just takes the distance x prime from the origin to the little element of charge. The element of charge, dq, is equal to lambda dx prime. So take the difference between these two vectors, and so it's this vector minus this one, so that's what we have here. And because we share these two terms, we can group those like this. So that's the vector r minus r prime, but what we really need is the magnitude of that difference. To find that, we can take the vector r minus r prime and dot it into itself, and then take the square root. And so that'll be then this quantity right here. Now we find the differential of the potential due to this little charge element. This will be the potential of a point charge, magnitude dq. So that's right here. So simplifying then, we know dq, we know the magnitude, we end up with this expression right here. Okay, so what I'd like to do now is switch to Mathematica. So here's our Mathematica program. So we've got the restatement of the problem up here, and this is our differential of potential. This is the same as we've written before, but I've replaced x prime with double x because Mathematica thinks that's a derivative. Xx is x prime, so dxx is dx prime. So we're going to integrate that. Here's the integral, so it's the same expression. The integral goes from minus L to L because that's the range of the x prime where the charge exists. And in order for Mathematica to speed up a little bit, I put in these assumptions. All they are that the parameters are all positive and they're all real. That saves some time during the integration. I'm not going to take that time. Here's the result of doing this integral. We get the log of the ratio of this expression here divided by this expression here. So I put that into the input. It's the same expression. I let L equals 1 because we want to plot it. You have to have only variables that can be handled, the x, y variables. You can't have any other. So here's the statement for the plot. Potential is what we're plotting. That's here. Here's the range of the two parameters, and the plot range in the z direction is the range over which the potential will change, starting at 0 and going up to 20. We could change that if we wish. And then we're going to take the contour plot. So here's the result of the 3D plot of the potential. So potential is in this direction. The line charge is down here in terms of its location. It goes from 1 to minus 1. This is turned around. Yeah, you don't like that? Well, okay, we'll turn it around. The plot goes from minus 2 to plus 2, and the line charge minus 1 to plus 1. So in this view here, you can see that where the line charge is, you have the potential going up as a function of xy. It goes up to a value which is highest. If we were to look at the dependence along the x-axis, you can see that it falls very rapidly, like this. It falls very rapidly on both sides. And now if we look in this direction here, we're looking now along the y-axis. Again, you can see that it falls rapidly, but not as rapidly as it does on the ends. If you were to convert this to a mountain, so this is the height, then you could see that if you're going to get off the mountain, let's say on skis, first of all you're going to kill yourself. But secondly, the slope in this direction changes the least, and in this direction, it changes the most. So I guess if you had to choose, you'd come down the mountain this way. Well, let's look at the contours, because what a contour is in this plot here would be a cross-section of potential at a constant value of the height. So in this case it would be the constant value of V. So if you took slices across here like this, you would get the contours. So let's look at it like this. You can see here that if you took a contour at constant height here, you might get something that is perhaps elliptical. And that's the case that you see here. So the line charge is between these 2 points here, like this, along the x-axis. This is the y-axis. And so as you look at the contours close to the line charge, they're ellipses. Because we've limited the height of the potential, we don't see any values here. But it would continue to climb steeper and steeper as it approaches the position of the line charge. I mentioned that the slope of the potential is least in this direction and the largest right in this region right here. You know that the lines of electric field are perpendicular to the contours, and that has to do with the fact that the E field is the gradient of the potential, minus actually. If you take a look at the E field in this region here, it would head off like this, and then would curve like that over to this direction here. If you go in this direction, same thing. If you go in this direction, it would be right along here. So you'd have an E field that would be heading in this direction here. Now remember that the magnitude of the E field is dependent on the rate of change of the potential. So you'd have an E field that's very large right here, and then quickly getting smaller and smaller. The same for over here. It would be larger here and small way out here because the spacing of the contours and therefore the slope is getting very, very small. We can extend this easily to 3 dimensions. To do that, you can take these plots here and rotate them about the x-axis. You would then generate the surfaces of constant potential. We can plot that. We'll take a look at it. We have to get the potential, and for 3 dimensions, so we add a z direction here in the plot, which is into the paper here. The z-axis addition gives us a term that is like the y dependence. To find that, you just have to draw the problem in 3 dimensions and show that that's the case. The simplest idea is that it's symmetric with respect to y and z. So we have just that additional term in the potential. What we're going to find is we can't plot that because you have a function of 3 dimensions. There's no dimension left, so you can't really plot it. But we can show that we get the contours in 3 dimensions, and those will allow us to see how the surfaces of constant potential look like. So it's a similar process. You make up your assumptions. Here's the function that we're going to find. So this is what we call potential. We'll just call it F. And notice that it goes again from minus L to L over the parameter that tells you where the charge elements are, and then the only difference is we've added this c squared term in that square root. Well, here's the output. As before, it's the difference of 2 logs. I've simplified that by just taking the ratio of the arguments for the logs. So now we're going to generate the contours. To do that, we again have to set L to some number. I set it equal to 1. I'm going to split the contour plots into the plus z direction and the minus z direction, and I'll show you why. So here they are, right here. And the reason that I split them is because the way they're plotted right here, you can't see inside. So this is one surface of potential. Now let me tip this up, and you can see contours surfaces at various values. In this case here it's very simple. I only chose 3 values. And the same goes for over here. These are mirror symmetries of each other. I've cut the egg in 2 so you can see the layers. The line of charge is between here and here, like this. Again, the line of charge is here. It'd be in the plane of this rectangle right here. As you increase x and y, then you find these surfaces very similar to the 2D plot. And if you want to see the 2D plot, let me see if I can get there. It would look like this. If you look at the edges of these contour surfaces, that would be the slice right through the z equals 0 plane to show you what the surfaces look like. The important thing to realize is that in 3D you have these contours of constant potential. The E fields will be in the direction perpendicular to these surfaces. We might want to consider taking a look at that. Let's interpret above. The above 3D plots are the surfaces for plus and minus z of constant potential, and these are called surface contours, and these are surrounding the finite wire on the inside of the half egg. The charge is oriented horizontally in this picture right here. Cut these in half so you can see inside, and you notice that the two plots are mirror images. And to rotate them back to the normal position, we basically do this rotation like that, and this rotation like that. And I don't have these perfectly aligned, but you see the point. That would be the normal, and in order to close the egg, we just would have to move these two together. Well, let's find the E fields. If we take a vector field in 3 dimensions, we can plot that in a way that we can get at least an idea what it looks like. I've defined the E field as the gradient of that scalar function. This is the potential. Again, I have to set L equal 1, then plot it. So the plot then is over x, y, and z. Well, the gradient is messy. It's right here. The terms are 3-dimensional, so it's a vector. So here's the x component. All of this is the y component, and all of this is the z component. So Mathematica does an attempt to show that, and the reason that this is so hard to show is because the intensity or the length of these vectors falls so quickly. So this is what it looks like. Let me just look down the line towards the line charge is right in the center here, and rotate it so it looks a little bit normal. So this would be looking right down the line charge. This is not easy. Okay, so right there we're doing our best. So the line charge is coming in and out of the paper, and the vectors, you can see that they have a tendency to curve a little bit here, and they're large right near the line charge, and then they fall off very, very quickly. So if we now look in this direction, I'll try to get this lined up. So now the line charge is right here, and you can see that as you go away from the center of the line charge, the field lines are bent away from the normal to the line charge. They go off in sort of parabola behavior, which, remember, they have to be normal to the eggs. So that's why they have this curvature. We found then in x, y, z, the 3 dimensions, the potential around this finite line charge, and we found the electric field by taking the gradient of that potential. Basically, that's the procedure that you have for trying to find a description of what happens around a charge distribution. It's fortunate that this one is doable in terms of the integrals. In some cases, you just simply can't do the integrals, so if you need to know this information, you would do it numerically. For any charge distribution, you can in fact do the numerical solution to find both the potential and the E field. Just to make that clear, if you find the potential numerically, you can also numerically differentiate that and find the E field.